All right, welcome back, everybody. So this is, I don't know if it's the second or third part, depends on how I edit the video, but this is part 2/3, where I just covered strong weak deactivators and orthopara, those resonance structures that pretty much form the basis of our reasoning behind everything. So now let's actually try applying it. Okay, so for the question, which of the following is more acidic, right? You have benzoic acids with a meta-bromo group and a meta-fluoro group. All right, well, which is more acidic? Well, what we're looking for is, well, if we're looking for acidity, let's identify our acidic hydrogen. So which of the following hydrogens will protonate? I know as hell it's not going to be the hydrogens that are on the benzene ring. It's probably going to be on the ones that are on the benzoic acid. So now let's decide which of the following is more acidic. Which has the greatest net pull away? So which of the so the most acidic compound will have the most electron density being pulled away from the hydrogen, because as more electron density is being pulled away from here, the more the proton will want to get the heck out of there. All right, so same stuff from semester 1. So the answer would be this one. It would be the meta-bromo group. You might be thinking, why is that? Well, let's think about it. So if the difference is between bromine and fluorine, I know that they are deactivating groups. They're deactivating because they pull electron density out of the ring. So this is the general gist. Like electron density is being pulled out of the ring. All right. And thus, if it's out of the ring, it's being pulled away from our benzoic acid. All right. Which one has the stronger pink pull? Which of the following has the strongest just general pull out of the aromatic ring? Because remember, an aromatic ring, that's just a ring of electrons. So which has the greatest pull? Well, let's look at that list. Oh, come on. I have to keep scrolling. Between fluorine and bromine, which one's more deactivating? It's going to be bromine. Bromine is lower on the list. It's going to be more deactivating. So if bromine is more deactivating, that means it's pulling more electron density out of the ring. So if that pull is significantly stronger, I don't know if it's how significant, but if it's stronger than fluorine, well, it's going to be more acidic because more electron density is being pulled away from that proton. All right. So now let's address phosphorus and sulfur. So how the hell does phosphorus and sulfur play into this? Well, in short, it's really easy. Phosphorus, just treat it as if it was nitrogen, and sulfur, treat it as if it was oxygen. So a thiol has the same properties, or pretty much similar properties, as OH. What does that mean? A thiol is like an OH, a strong activator. Okay, it's a strong activator, so it likes orthopara. pH2, treat it like aniline. NH2. Lone pair. Let's drop the lone pairs. It's same properties, still strong activator like NH2. It's treated the same. So let's look at this. If we're trying to analyze which of the following hydrogens will be pulled off in an electrophilic aromatic substitution, essentially, where will the electrophile add? Where will the electrophile add? Well, let's identify our groups. So we have a moderate activator and a not moderate. This is going to be a strong activator right here. It's going to be a weak activator. You might be thinking, how the hell is PHCH3 a strong activator? Well, like I said up here, treat phosphorus as if it was nitrogen. So what I showed down there should have the same strength as an NHCH3 or an NHR. All right, because that's CH3 is going to be an R group. So it's pretty much the same thing as that. Well, treat it as it is. Strong activator. Phosphorus has the same properties as nitrogen. So a strong activator, a weak activator. So both want orthopara, right? So if it both wants orthopara, well, let's go with the strong activator. Well, actually, no, let's just disregard that entirely. Generally, the highest on the list will be directing your electrophilic aromatic substitution. So which is higher on the list? the strongest activator is higher on the list, so it's going to have more pull in directing. So you have your ortho groups and your para groups. However, something I do want to note, this is sterically hindered. You cannot go there. That hydrogen will not be pulled off. That is sterically hindered. So your two options are going to be right here. Okay. Now let's look over here. You have two nitrogen groups and a chloro group. All right. Where will the electrophile add? So let's think. You have a chloro group right here that wants to add ortho and para. Well, this para group and that ortho group is already taken, can't really add there. There's no hydrogens to pull off. But there's still that one ortho group over here. Now for that nitrogen group, it wants meta. So for this nitrogen, meta is right here and meta is right here. Right? Well, this meta on the right is already taken up, so it can't really add there. Now let's look at the nitrogen over here. It wants meta over here and meta over here. But we can't really add the meta there because there's already a nitro group there. Well, lo and behold, all three groups really want to add to this carbon. All three agree they want it there. So it's safe to say that's where we're going to probably add our hydrogen. Oh, shit, what did I just do? Now let's look over here. Okay, which of the following is higher on our table? So we're looking at the strongest activator to the strongest deactivator. Whichever one's higher on the list is our directing group. So if we have a moderate activator versus a weak activator, the moderate activator is higher on the list, so it'll direct pretty much everything. So out of these, we have a weak activator, weak deactivator, and then we have a strong deactivator. So our weak activator, that's going to be directing. So once I have ortho para, so it's going to want to add here, it's going to want to add here. Okay. So if it wants to add there, well, it also wants to add here for ortho, but that's spot's already taken. The weak deactivator also wants ortho para. It's going to want it right here, and right here. But again, can't really add it in either of these two spots that I just erased. And then this nitro group will want to add this meta and this meta. Okay. Well, can't really add there. So if we're looking at these, well, where do we add the electrophilic aromatic substitution? Well, the highest on the list will be directing. So it's going to be weak activator. So I don't want these. We're going to be following this because this is the ortho para for our highest substituent group, which is our weak activator. Now let's look over here. SH and CH3. Let's identify. We have a weak activator, strong activator. I'm thinking, how is SH a strong activator? Well, sulfur follows the same rules as oxygen. So treat it as if it were oxygen. So if I know OH is a strong, if OH is a strong activator, SH must also be a strong activator. So this strong activator right here would want ortho para. You're welcome to just leave it at that. This weak activator would want ortho and para. Same thing with this ortho over here, but there's already something there. Don't worry. So out of these two, which one will we go with? Well, whichever one's stronger, the stronger activator is going to be SH. So these two spots are going to be pushed. Let's look over here. All right, NCH32. All right, this is a lot similar to one of your problem sets. Or one or two groups problem sets. NH2, lone pair, right? So NR2 is kind of similar to NH2 or NHR, also similar to NH2 as substituents. Because of the fact that they have the nitrogen directly attached to the benzene ring, it means it can donate that lone pair. So if it can do that, we know that it wants to do an ortho pair, because if that substituent atom has a lone pair, it'll want to donate and form ortho para. So where do we want ortho para? Right here. Now, you might be thinking, isn't there a steric hindrance for the ortho groups? You're right, there is. But it's so fine. So these three are all valid spots. All right. So if you're asked which of the following hydrogens is available for electrophilic aromatic substitution, you would put an arrow for all of them. If you're doing predict the product, right? If you're trying to take this and trying to react it with, let's say, Cl2FeCl3, all right? If it's predict the product, you only need one product. So it'll preface, or the test will preface, if there's two products, pick the best one. And which of these will be the best one? It would be the para, because compared to the ortho, it is less sterically hindered. So for predict the product, if you had to pick one, pick the para. But if it's just straight up asking you which of the following are eligible hydrogens that can be removed in an electrophilic aromatic substitution, you just do all three. Now, the times where you wouldn't do that are the unreasonable reasons. So the first one we've already encountered. If you have a hydrogen, right? Because remember, this is still benzene, you have a hydrogen that's between two groups, it's sterically hindered. It can't be really reached as well. So this automatically, no, it cannot be taken unless it absolutely has to, but thermodynamically, it's going to prefer the other two spots a lot more. Like that hydrogen that I just crossed off, it might be substituted in like 0.05% of your product, but it's going to be so negligible. Another reason that I could think of is if you had like a terp-butyl group. CH3, CH3, CH3. All right. So you have an R group, an alkyl group. You know that's orthopara directing because that is a weak activator. So ortho, para. Which of the following is eligible? I would probably only mention the para because terp-butyl groups, they are so sterically hindered that ortho group's not going to do much. It might substitute in the ortho position, maybe like 2% of your product, maybe, I don't know, but don't worry about it. Let's move on to over here. So you have an aniline and then you have a C terminus on an ester. Which of the following spots is best for electrophilic aromatic substitution? Which hydrogen is better taken off? So whichever one's higher on the list will be directing. So if aniline is a strong activator and this ester is a moderate deactivator, because remember, it's on that C terminus, not the O. If it was on the O, it would be moderate activator. All right. Which one's higher on the list? It's going to be an aniline. Aniline will want to do ortho and para over here. While the moderate deactivator would want to do meta right here, right here. Well, would you look at that? Your ortho, para, and your metas, they agree. So both of your groups will want to favor stuff being put right here. This is what we want. And that's just how you would leave it. All right. Now let's go over here. Now, if you're given this, which of the following of the four reacts fastest to electrophilic aromatic substitution and which one reacts slowest? So if you remember all the way up here, right, on speed, the activating speeds up the reaction, deactivating slows down the reaction. So the net activation rate is kind of proportional to your reaction rate. So the more activated it is, the faster it is. And the more deactivated it is, the slower it is. So let's use our values, because remember, the kind of like the money system where strong activators like a value of 10, moderate activators value of 5, weak activators a value of 1. Just your normal benzene is just 0. Weak deactivators -1, weak, not weak, moderate deactivator is -5, and then strong deactivator is -10. So in that logic, let's look over here. OH and OCH3, that is a strong activator. Strong activator is going to have a value of relatively +20. OH is a strong activator. So relative value +10. Over here, we have a strong activator, weak activator, +10, +1, value of, these are supposed to be squiggles, of around +11. Strong activator, weak deactivator, +10, -1. That's going to be -+9. Let's be +9. So which one's the fastest is going to be the highest value. So this one right here is the most activated, while this one on the right is the most deactivated. Simple enough. Okay. I don't know where I was going with this one. I don't know why I drew this one. Yeah. Oh, yeah, I remember now. Now, if you're asked to decide which of the following out of these two reacts the fastest, well, let's look at our values. So we're looking at the most activated. So this is a strong activator. The O terminus, the one with the lone pairs on that, I'm supposed to be no here. That's a group. Okay. No, that's actually right. There you go. That's gonna be positive 10. So net value of positive 10. I think this is supposed to be, let's do a CH3 CO. Okay. So an OH is a strong activator. CH3 is a weak activator, weak deactivator for chlorine. This is going to be positive 10, positive 1, minus 1, approximately positive 10. How the hell do I differentiate? Which one's faster? Can't really tell. Straight up, I'm going to tell you right now, it's a tie. So either way, you can put it, you can rank this 1, 2, or 2, 1. We won't throw that on the test. It is on the problem set, but we won't do something this tricky on the test. We'll be pretty concrete about it on the test. All right, I'm going to stop my share. That was a long time. Just for your guys' reference, I think I was recording about an hour and 15 minutes, maybe a little longer. I don't know, plus my editing. Anywho, I'm tired. I'm going to go to bed. Good night.